this lecture, we are going to move on to activated carbons. So activated carbons are formed, these are also a form of non-graphitizing carbons, and they are formed by the charring process that you know already. The fact is that the polymer precursor does not undergo a semi-solid phase after its degradation, and that is why, even though there will be some shrinkage, but there will be more pores rather than shrinkage in these carbons, because the skeleton of the polymer is preserved more or less. So natural polymers such as wood, or the seeds of fruits, or many cellulosic natural fibrous materials, polymers would typically yield porous carbons. So why do we say porous is activated, and what does it mean to be active? First of all, what is an active surface? Surface that is working out, very active. Not really. The point is that active surface is something which has certain chemical groups which render it active. So either because of these chemical surface functional groups, or because of porosity, which is a physical property, or a combination of both, these surfaces have the ability to bind, or at least form weak bonds with any chemical or biochemical entity, which means they can absorb these things onto their surface. So this absorbance is what makes them active. That is why we call them active carbons. Okay. Now, important thing is that active carbons are very important industrial materials. So about 30% of carbon related research, and also of course a lot of industrial applications, are all related to activated carbons even today. So even though we have a lot of carbon nanomaterials, and there are for electronic device applications and so on, we are working more on the nanomaterials or advanced materials, but for a number of adsorbents are always important. So water filtration columns, for example, they have always been there, and they are very important. Nowadays also we have this zero waste water policy from the so the water from the chemical industries should be completely clean. So these kind of policies are now coming up all over the world. The point is that how do you clean that water? The industrial wastewater, or the household wastewater, or the drinking water? All kinds of water purifiers are they are made of activated carbons. They're predominantly made of activated carbons. There are also some other materials such as zeolites which are used here and there, but they are relatively much more expensive. And we already understand the technology related to activated carbon very well. We know the adsorbance mechanism and so on. So still predominantly these are the carbon materials which are used for filtration applications. Not just water filtration, also air filtration and so on, we will see. So the point is that this remains a very important industrial carbon material as on date. Okay, so this is an image where I have shown, there are three images here. So in number A, you will see that this is if you go and buy activated carbons, you will either I think I've shown this picture before, that you get the cylinders, or you also get powders and so on. So they look like this. There's a grayish color, no shine and luster, similar to glass-like carbons because of the porosity. So this is the kind of carbon you will be able to buy. Okay. Now also coals are, some types of coals and charcoal, these are also porous materials, so they look very similar. Okay, but if something is porous, that does not necessarily mean it is activated. Okay. Now, however, let's first talk about the porosity in these carbons. So in this image B, what you see is how the pores go inside. This is the structure of the pores in these active or porous carbons. So this is, for example, a wood-derived carbon. So if you see a lot of natural polymers, natural structures, they have this what is known as fractal-like geometry. And you can see then there are some larger pores, and then the smaller ones, they branch out in a way, and then the smaller and smaller and smaller pores, which kind of have a self-replicating structure or self-similarity. Okay, so now because of this kind of structure, you can already see that if there is any molecule, it can get adsorbed on top of it can go inside one pore, the biggest one, and or the smaller one, or the further smaller one, and so on. And even very small molecules can get can get inside, they can get absorbed. Now the difference between activated carbons and anything formed by coking, for example glass-like carbon, there you have nanoscale pores, but they are closed pores. They are these fullerene-like structures, so nothing can go inside them. At least a lot of pores are closed pores, but here in this case you have open pores, pores that are percolated, pores that are connected to each other. So there is a sort of path then the adsorbate molecule can take and can go deep inside. So the pores have these fractal structures, and so a lot of things can get absorbed on top of them. For example, heavy metal ions, which you often find in water, becomes very important during water purification. Various microbes, bacteria, and so on, and the number of small molecules and biomolecules can get trapped inside these pores, so to say. Okay, now it's, as I said, that a lot of materials that are formed by charring, carbon materials, they are porous, but what you also do is you do certain activation processes that we will come to. Okay, now as I mentioned, the pores have fractal geometry. What does this mean? They have different pore dimensions. So they have micropores, mesopores, and macropores. So what do these pores mean? I think we earlier discussed that micropores is not microscale pores, they are nanoscale pores. Actually, all of these are mostly, when we talk about porosity, we are mostly talking about pores that are in the nanometer scale. Okay, macropores, however, the largest ones, if something you can see on a carbon material or you can observe in a standard optical microscope, those things would be definitely larger than 50 nanometer. So anything that is larger than 50 nanometer, you call them macropores, which is shown with number 1 in this image, B. Okay, the second type, the number 2, is the slightly smaller version. So these are the pores between 2 to 50 nanometers. So in terms of their diameter, if we consider an equivalent sphere. So these are called mesopores. Okay, the smallest ones, which are of 2 nanometer diameter range, they are called micropores. So I mentioned that it is 2 nanometer range. So typically in the literature you will find even people up to 5 nanometer pores are sometimes called micropores. But as per the IUPAC definition, it should be the pores that are smaller than 2 nanometer in diameter, they should be called micropores. In fact, these micropores are then further divided into super micropores and ultra micropores, I think, basically based on their diameters. If they are between 0.7 nanometer to 2 nanometer, and then these are super micropores, and then the ones that are smaller than even 0.7 nanometer molecular length scales, they are known as the ultra micropores. Okay, now what are these fractal geometries? Let me quickly tell you. Okay, so what are fractal structures again? The structure that I have shown you for the porosity of carbon structures, so we will only talk about the context of porous carbons. So you see these kind of branches in these structures. Okay, now if I take one of these branches and I zoom in, then what I'm going to get is I'm going to get something which is very similar, the geometry that is very similar. So these are basically known as self-symmetric structures. Again, if I take another branch, then zoom in further, then I will get the same kind of structure. So these kind of structures are basically known as fractal geometries. Now fractal geometries are used not just by scientists, but to understand a lot of natural materials, but also by artists. So a lot of computer generated art is nowadays based on fractal structure. So if you're further interested, of course you can read more about it. Very briefly I will let you know, if you want to mathematically represent these kind of structures, then this is the representation. So Zn plus 1 equals Z
n square plus c, where c is a constant and n, this is the number of sequence, and z is any complex number. So in this formula you can put in any complex number of the form x plus jy, and then you can get the n plus first term. Okay, so this is how you can keep on calculating. Basically, your next term is going to have the self symmetry to the current term. Now, most of the natural structures are not perfect fractals. So these repeating units that I have shown here, they may not be exactly the same as the previous structure, but they are approximate, and they have approximate symmetries in the case of most of the natural structures. But of course, in the case of computer generated art, you have these perfectly symmetrical structures. Now, if you are interested, as I mentioned, you can read more about what is known as a Julia set and what is known as Mandelbrot set. These are the basically, in one case you have C as constant, and in the other case C is allowed to change, and so on. So this is a field of research in itself. So you can read more about it. For us, what is important is that we have these fractal-like geometries in the pores of many natural polymers, and that is why also in the porous carbon, after carbonization, we get these kind of geometries.
Okay, so now since we already have these the porosity in these carbon materials, they can, even without the activation, even when they just come out of the furnace, they can absorb some things. So they do have the geometry to trap the molecules, which can be molecules of a gas, of a liquid, or they can also be some other biological entities, for example. So the point is that their geometric structure already enables them to trap these molecules. However, now we can further enhance this absorbance by what is known as the activation process. That is why these carbons are known as activated carbons. They are not known as active carbons, although you will occasionally hear this term. But the point is that when we are performing the activation process, then we call these carbons activated carbons. Okay. Now, how do you do the activation? So there are certain physical methods, and there are also certain chemical methods that we are going to talk about. But what you need to understand is, what does it do? The activation process, it generates more micropores. Micropores, again, they are smaller than 2 nanometers. So these tiny pores, then the activation process generates many more of them. So initially, when your carbon comes out of the furnace, when it has this fractal geometry of pores and so on, let's say wood-derived carbon, it will have all sorts of pores in pretty much similar fraction. But after the activation process, now the micropores will dominate. So the number of, or the fraction of micropores becomes much higher. So that is what happens by the activation process, and then you calculate the porosity. Okay. Now, what is important for us is the surface area that is available. Because you see, now we are doing adsorption. So whatever surface area, the more the better, the surface area that is available to us. So that becomes an important parameter, and the total open pore volume. So if you have closed pores, they are not useful for you. So these are the two important factors. Now we need to increase these two things. We need to increase the surface area, and we need to increase the open pore volume. Okay. Now, as I mentioned that this is we are doing this artificial activation in many cases. So what you can also do is, you can do activation of glassy carbon, you can do activation of other types of carbons also, and then you can also call them activated carbon. The point is that there is no point in doing it, because you see, this pore structure that we already have a lot. If we want to use this material as an adsorbent, then we need to have these open and percolated pores. Because if you activate the glassy carbon surface, which people are doing, for example, if you want to attach a certain other chemical on top of it, because glassy carbon is generally very inert, so it's very difficult to attach anything on top of it. So you can do some physical and chemical activation, and then that is often known as not activation but surface modification. Because it is happening only on the surface, only at the surface, and not inside the material. But for the adsorbent fabrication, it makes much more sense to activate the porous carbons. Okay. Now, one more thing, as I'm using now exchangeably the terms porous carbons and activated carbon, but they are not the same. So porous carbon is what, the carbon structure that you get after the charring process. But when you further do the chemical or physical activation and increase the number of micropores, that is known as, that is the activation process. However, industrially, the term activated carbon is used when the purity of the carbon is also high enough. So in many low temperature carbonization processes, you will get certain types of chars. So these are also very porous, but their purity is pretty low. So in the case of industrial applications, you will call it activated carbon when it is at least 98% in terms of its purity, which means also that the temperature should be reasonably high. So let us now talk about the activation methods. So I told you that there are, you can do physical activation, chemical activation. So what does the activation do? Number one, it increases the microporosity. Microporosity increment means that the surface area, net available surface area, is being increased. Okay. What it also does is it will induce the activation process, especially in the case of chemical activation process. You may end up getting certain active surface functional groups. So these are chemical groups which have the ability to attract molecules. So they are typically radicals. They are oxygenated functional groups. They can be various functional groups. Because in most cases you will use these activated carbons for absorbing things that are hydrophilic or that are present in water, or even anything that is biological. They are typically hydrophilic molecules. So you will often induce hydrophilic surface functional groups on top of these by the activation process. So these are the two things that actually take place. Now, as I said, that the microporosity or any kind of porosity is directly related to the surface area. So this is something very easy to understand. This is, let's say, a very flat surface, this line. The second one is a little bit rough surface. So you can have these holes, pits, or you can also have hill-like structures. Basically, you have certain roughness on top of on your surface. In that case, you have a higher surface area. If you had to walk on this, you will have to now walk more. Now, if I have the structure, which is what we have in the case of natural porous carbons, then you see that the surface area is so much more, several times more. So that is how surface area increases with porosity. Okay. Now let's talk about the activation methods. The physical activation, basically, first of all, when you get these porous carbons, let's say I prepared my porous carbon or some sort of charry material, let's say even if I made it from the waste material, agricultural waste and so on, and I prepared it at not very high temperatures, which is often the case with porous carbons. They are not prepared, at least initially, at a very high temperature. There is a reason for that. If you keep on increasing the graphitic content, so you know that if we increase the pyrolysis temperature, then the graphitic content increases, and more graphitization basically would mean that the surface becomes more inactive, and then you also get harder carbons and you actually lose porosity at a certain point. So you don't go for very high pyrolysis temperatures, but let's say between 800 and 1000. Now, in that case, you get reasonably good porosity, but the problem is that you may still have some of this, byproduct. So tarry byproducts you might still have, which may coat the surface of your pores. So in that case, number one, option, the first thing that you will do in the name of physical activation is to again perform the heat treatment in inert atmosphere. What you're trying to do here is to get rid of this tar which was on the surface. So basically now you get more surface area. The pores that were blocked by the tars, they open. So that is one method of physical activation, which is often often done. It is in most of the cases. Okay. Now, one more physical activation method is that you take an oxidizing agent. Oxidizing agent is something that contains oxygen. So for example, air or steam or carbon dioxide, often a mixture of these things. So steam plus carbon dioxide, for example, you will have this inside your furnace when you heat treat it. And this heat treatment again is not performed at very high temperatures, but between 800 and 1000. So this kind of activation, what does it do? It leads gasification or oxidation of some of the carbons. So some of the carbon from your carbon material will now, because it has oxygen, right? So you know that when you have oxygen, then there is a possibility of oxidation of carbon, the formation of carbon dioxide. But at the same time, you also have the steam over there. Now, water molecules are smaller than carbon dioxide molecules, so they actually diffuse inside these extremely small pores that you have. So that sort of blocks further gasification. So when you perform the pyrolysis in steam, then you end up getting these highly porous carbons, but you must remember that because there is some gasification or oxide formation is happening, you do lose some carbon. So actually, the time of carbonization is often, or time of activation must be optimized. So if you perform activation for a very long time, then you may end up losing a lot of carbon mass. Okay. Now coming to chemical activation methods. Okay, as the name suggests, you're adding certain chemical, but at what stage? This kind of activation is often performed for wood or other natural materials, so biological based and so on, natural polymers. Okay, now what you do is you actually add a certain chemical before the pyrolysis. So when you just have a piece of wood, you will first add certain chemical to it, and there is a long list of such chemicals. So there's strong acids, and then you have metal hydroxide, chlorides, carbonates, and so on. These agents these are dehydrating agents, and these agents basically, they partially degrade the cellulose even before it is taken for carbonization. Okay, and now you perform the pyrolysis, and that is when you get an enhanced surface area. Okay, so these two are the there are many other methods also. There are various advanced porosity or the activation methods where you may also utilize the combination of both. Here and there you will also do plasma activation, so plasma etching of the surface, which is also done, for example, for device applications for glass-like carbons and so on. So all of these are, there are various activation methods for making your carbon more, for increasing its absorbance. Okay. Now, once you have this, how do you measure the porosity? We will also learn about this in the when we learn about characterization technique. There are some standard processes. The most common process in the case of carbon porosity measurement is known as gas adsorption isotherms, and this is also known as BET method. We will talk about this. There is something known as mercury porosimetry. Then you can also perform X-ray tomography, other imaging techniques, even magnetic resonance imaging, MRI can give you porosity values. Okay. Now, this I have already told you that other types of carbons can also be activated, but for industrial adsorbent application, why would you do that? You rather will use relatively cheaper char-like carbon, which already has a lot of porosity, and then you will perform the activation for that. Okay, so what is the adsorption mechanism? And also we'll talk about some of the applications here. Before that, so I have already mentioned to you that the heat treatment is sometimes performed at lower temperatures, 800, 900, 1000 degrees, just to avoid making the carbon very hard. By the way, a lot of non-graphitizing carbons are also known as hard carbons because they are hard and brittle as compared to graphite, which is soft because of the layered structures. Okay, so the polymer, the carbon becomes harder if you increase the heat treatment temperature. So you would often get them at lower temperatures. That also reduces the cost of these kind of carbons. And then, however, because of these, a little bit of tar that is left over, in order to get rid of that, you will further heat treat it. Now, the important thing here is that if you understand the mechanism of pyrolysis of these kind of carbons, the framework of these pores is already formed at around between 500 and 600 degrees. So there you already have a good porous network. Before that, the material may still be arranging itself, or it may still not have the good carbon backbone, well-defined carbon backbones. But at 500, 600, even though you do have a lot of impurities, you understand that even pyrolysis goes on till 700 typically. So you have still a lot of impurities, but you do get the pore network. So you can basically stop your heat treatment at some point after this. So often it is done, to 800 degrees initially, and then reheat treatment after cooling down. Okay. So yeah. Now the important thing is that also I told you that activated carbons need to have 98% purity. Now if you have low pyrolysis temperatures, then you will not get the desired purity. So now what you need to do is you need to figure out the trade-off. You need to find out what is important for you. If the purity is very important, then you will keep on heating the material. Also, if in a certain case, for example, if you're using this for energy storage application, and you also need a good electrical conductivity, in that case you need to go to higher pyrolysis temperatures. But if you're making a filtration column where a reasonable purity, let's say 96%, is all right for you, in that case what is more important, you don't care about the whether you have short range order or not, and what is the LA-LC value, what is the electrical conductivity, you don't really care. You rather care about the good porous network. So depending upon that, you will determine your heat treatment temperature. Okay, so now we talk about the adsorption mechanism. Now you will say that this is simple, right? If you have an active surface, certain functional groups that can attract the molecules of whatever is being adsorbed, then those molecules will just come and they will deposit on top of the surface. Now this can happen due to both physical and chemical reasons. Physical reasons, if you have the pores which are of the size of the molecule itself, or you want to, let's say, in order to control environmental pollution or the pollution of water, drinking water, with nanoparticles, which is, by the way, a big problem nowadays. You have a lot of nanoparticles in the cosmetics. When you wash your face, then these particles get mixed into the water and then finally into the groundwater and so on. So if you want to remove these nanoparticles, in that, maybe the size of the nanoparticles is of the same range as the pores, the micropores. So in that case, this can also be a physical trapping. So in most cases, it is a combination of both physical trapping and chemical attractive forces, which can be due to because of the fact that you have radicals on the surface, or just they may also be weak van der Waals forces. Okay, now the point is that you may have either a single layer of these molecules that are adsorbed, or you can also have multiple layer, and this is important because that determines how your adsorption isotherms look like. So you can have these two types of mechanisms of the adsorption on top of the surface. Okay, and that will actually depend upon the molecule that is being adsorbed. What are the properties of that molecule? Okay, so now yeah, as I said, that hydrophilic functional groups will attract the water molecules. And generally, because most of the applications require water-related, molecules or hydrophilic molecules, then typically you will have hydrophilic surface. Okay, now coming to the applications. So water filtration, I already told you. There are also air purifiers. Right nowadays, actually, you can buy a lot of purifiers, for removing odor, removing, color from things that are mixed in water, anything that is because of the organic molecules. So for example, in a restaurant, you get a lot of food of smell, even because there is food being cooked all the time. So in the kitchens of various places, you may find some bag hanging there, which is just there to remove the odor. Okay, these bags would contain basically activated carbons. You can also buy something for your car exhaust, which absorbs fumes and it's at least a few organic materials, unburnt tar-like materials that are coming out of your car. So all of these kind of, for various absorbent applications, you're using activated carbons. Also in the pharmaceutical industry, this is used. Energy storage devices is also, so energy storage devices are batteries and supercapacitors. In this case, surface area is very important. In that case also you use electrodes made of activated carbons. You often have reasonable electrical conductivity in this case. Okay, now one more very important application is the use of activated carbon as catalytic beds. So what are catalytic beds? You know that in a chemical reaction, if you add catalyst, then the reaction rate increases because the activation energy goes down. Okay, and the point is that you can just, in the solution, let's say you have in a certain solvent, you have two chemicals mixed, and you can also add your catalyst in the same solution. or you can also provide a solid support for this reaction. So you take an activated carbon bed, on top of that you add both your reactants and you also add the catalyst, and then what will happen is this increases the residence time. Residence time means the time that where your all three entities can interact. Because in the solution they are always moving, but here they have a solid support. And solid support, of course, again, if you have pores of this kind, then inside these pores you can trap the molecules of whatever reactants you have, and also the catalyst. Or sometimes you can already load your catalyst. Loading means you already have the catalyst on top of your activated carbon surface. Because of the porosity, it will also go all deep inside the pores and everywhere. And now on top of that bed, when you perform your reaction, then then the catalyst has a more surface area of the catalyst is also available to catalyze the reaction. So this is also an industrial application of activated carbons, by the way. Okay. Now also, yeah, one important thing is that the catalytic bed should itself not participate in the reaction. Given the fact that in general carbon is unreactive, so its surface is active, but it will not degrade, it will not corrode, it will not participate in the reaction by itself. That's why it makes a very good catalytic bed. Okay. Now, just based on the available types of activated carbons, we can also classify them. So depending upon what is available, for example, in the market, you have powdered activated carbons, you have the cylinder-like structures, you have also what is known as granulated activated carbons. So grains are larger than powders. So the grains are, in this case, you will find yeah, you can have spherical particles, you can have cylindrical particles, you have basically grains, granulated particles. Also sometimes they are randomly shaped grains of activated carbon. And spherical, as I already mentioned, you also can have impregnated activated carbon. Impregnated means you already load something, let's say a metal ion, on top of these activated carbons. These are typically used for catalytic beds and other chemical reactions. Okay, and then you also have some other advanced versions like polymer coated activated carbons and so on. That depends that is very specific to the application area. So why would you do polymer coating? Then you are kind of reducing the active surface. Well, you often use these things for biological applications. So you will have a biocompatible polymer coated on top of the surface, so that so these are for biological applications. Porosity, the porous network you are still using. So these carbons, they are sort of porous carbons, but they are coated with polymers. So this is a different activation method. Activation can be done in any desired way, whatever you want from the surface. Okay. What is also very important, this is something we are going to learn in the carbon fiber section, that we can activate the carbon fibers as well. Carbon fibers, of course, some of them are made of natural polymers like cellulose, and they are also made of some synthetic polymers. We will talk about them. So activated carbon fibers is also a very interesting field, because carbon fibers already offer a lot of surface area compared to a bulk solid, and if you further activate them, then you have a very large surface area available, and then you can make really a very high efficiency adsorbent structures. Okay, now, yeah, one more thing, if you're further interested, this is a wonderful paper by Dr. Satish Manocha, and there are also several lectures available on NPTEL as well as other open sources. Okay.